Hi, my name is Lola Reyes, and for my math review project, I decided to choose the topic of graphing polynomial functions, which is chapter 2 in the book. The objective of this video is to help you guys understand the aspects of polynomial functions and how to graph a function. Firstly, there are different types of polynomial functions, that of which depend on the degree of the leading coefficient, which is the term in a function that has the highest power of x. In this video, I'll just be focusing on quadratic and cubic equations, which have degrees of 2 and 3, because they are the most commonly used types of polynomials. I just pulled examples of these functions from page 53 in the textbook to elaborate back on the idea of a leading coefficient. So if we were to take the leading terms from these two functions and compare them to each other, the cubic function's leading term would be considered the leading term between the two because it has the highest power of x, which is 3. So when you encounter a polynomial function that you need to graph, the first thing that you want to do is find the y and x intercepts and their multiplicities, but I'll be elaborating more on the concept of multiplicities after I find the y and x intercepts. For this example, I'll be using the function f of x equals x minus 5 times x plus 2 squared because it's easier to understand. I'll usually start with finding the y-intercept, in which case you substitute 0 for all the x's and just solve for f of 0, or aka y. So first we do f of 0 equals 0 minus 5 times 0 plus 2 squared, which comes down to negative 5 times 4, in which we get negative 20. So here is our y-intercept. Next, we'll be looking for the x-intercepts, where f of x will equal 0. So this will look like x minus 5 times x plus 2 squared equals 0. And then we use the zero product property, in which we basically split these two parentheses by themselves and make them equal 0. So that would look like x minus 5 equals 0 and x plus 2 equals 0. Then we just solved each equation, where we would add 5 over here and x would equal 5. And then we would subtract 2 over here, and x would equal negative 2. So these two, 5 and negative 2, are our x-intercepts. Now we need to look at the multiplicity of each 0, which mathematically is how many times a particular number is a 0 for a given polynomial, but in simple terms just tells us how the line of the polynomial will react to the intercept. I decided to take a diagram off the internet to give a clear explanation on how multiplicities affect the graph. So, a 0 with a multiplicity of 1 will allow the function to go straight through the intercept. A 0 with a multiplicity of 2 will cause the function to bounce off the intercept, and a 0 with a multiplicity of 3 will allow the function to go through the intercept, but at somewhat of a curve. So in our example, the x-intercept has a multiplicity of 1, which you have to kind of imagine, as well as a multiplicity of 2. So specifically, the x-intercept 5 has a multiplicity of 1, and the x-intercept negative 2 has a multiplicity of 2. So the line will end up crossing through 5 on the x-axis, which I have my graph here. It will cross through 5 on the x-axis, but it will end up bouncing off of negative 2 because it has a multiplicity of 2. So it'll be like that. And we know it's going to go this way rather than that way because we have a y-intercept of negative 20 down here. So it will touch there and then go back up to 5. So next, you'll need to find the end behavior of the function. The end behavior is most dependent on the leading term within the equation, so we'll need to change the equation to standard form, which is basically solving it. So first we'll need to do x plus 2 squared, which is x squared plus 2x plus 2x plus 4. And so we can add that to our equation, which is f of x equals x minus 5 times x squared plus 2x, or actually plus 4x, because we can just add those two 2x's together, plus 4. So now we need to multiply both the x and the negative 5 individually into these three terms. So multiplying by x first, we get x to the third plus 4x squared plus 4x, and then multiplying this by negative 5, we get negative 5x squared minus 20x minus 20. And then we can simplify this by combining terms. So we would get x to the third minus x squared minus 16x minus 20. And this is what standard form for this function would look like. Here's a diagram that I started to draw but haven't completely filled in that shows the end behavior based on whether the leading term has a positive or negative coefficient and whether the degree is odd or even. So with an even degree and a positive leading coefficient, the graph will look like this. It's going to be symmetrical and it will be going up both ways. On an odd degree positive leading coefficient graph, it'll look like this. One side is going up, but the other side is going down. It starts down, but then it goes up, is what I mean. And then for an even degree negative leading coefficient, it'll be going down on both sides, but it still makes a symmetrical shape. And then for a odd degree negative leading coefficient, it's going to start up, but then it'll start going down, like it did on this one. So comparing our leading coefficient, or leading term, with the graphs of this diagram, it has a positive leading coefficient with an odd degree, so it will be matching the end behavior of this graph. So now that we know the end behavior, the multiplicities, and the intercepts of our graph, we're able to finally graph our equation. So basically it will look something like this. Hold on. There you go. So here I have a somewhat more difficult equation that we can solve, just because it has larger terms at the end, 32, and it also doesn't automatically tell us what the x-intercepts will be because it's in standard form. So first let's start with solving the y-intercept. So we can do this by making all the x's equal to 0. So f of 0 equals 2 times 0 to the third minus 2 times 0 to the second minus 32 times 0 plus 32. And that means all of these cancel out and f of 0 would equal 32, making our y-intercept 32. Next, to find the x-intercepts, like I said before, our equation doesn't give us the zero product property, or doesn't show us it automatically, so we have to find that out. So to do this, we can make our equation equal to 0. So 2x to the third minus 2x squared minus 32x plus 32. And now we can divide each equation or each term by 2 because they all have that in common as a factor. So 0 divided by 2 would just be 0. That'd be x to the third minus x squared minus 16x plus 16. And now that you're looking at the terms, you might see that both of the paired terms have a coefficient in common, so we can factor these terms out. So 0 equals x squared times x minus 1 minus 16 times x minus 1. And then you kind of just simplify x minus 1 and x squared minus 16. And notice that x squared will help when we square root the negative 16. That will help make a positive 4 and a negative 4 for our x-intercepts. So 0, we can separate these, but first let's just do x minus 1 times x minus 4 times x plus 4. And now we make all of these equal to 0. And just solve. So our x-intercepts are 1, 4, and negative 4. You can also notice that none of these parentheses here have multiplicities on them, so that means that the line of the equation will just go straight through them rather than bouncing off of them. So finally, with our function, we can see that the coefficient is positive and the degree is odd. So our graph will end up looking with an end behavior of this. So, using our x-intercepts and y-intercept, we'll get something that looks similar to this. So one common mistake